Why do protons and neutrons, which form the building blocks of atomic nuclei, remain so tightly bound together? Why can't they be easily pulled apart or pushed away from each other? In the energy filament theory, the strong force isn't just some mysterious force pushing objects around. Rather, it emerges as a deep consequence of the structure of the energy sea. The essence of the strong force lies in its relationship with tension gaps. When you attempt to pull apart a structure at a small scale, the energy sea responds by locking the tension and filling in any gaps that might form. What seems like a powerful, short-range attraction between particles is actually the energy sea's way of managing and redistributing the forces involved, ensuring that the system remains in its most stable, energy-efficient state. In textbooks, the explanation of the strong force typically begins with quarks. Inside nucleons, quarks interact by exchanging gluons, which are the carriers of the strong force. These gluons create short-range forces that result in nucleons remaining bound tightly together, while also exhibiting extreme repulsion at very short distances. You are likely familiar with terms like confinement and saturation associated with the strong forces. But despite the elegant formulas and experimental validation, these concepts don't really paint a vivid picture of what's happening. It leaves you asking questions like, why does gluon exchange lead to increasing tension between particles? Why is it impossible to separate a quark from the other quarks in the same particle? Are gluons particles themselves, or are they something else? What exactly is the true nature of the strong force? According to the energy filament theory, quarks aren't simply tiny point-like particles. Instead, they are microscopic loops of energy filaments, each carrying a tension pattern, a texture that defines their behavior. Imagine a quark as a tiny, twisted loop embedded in a fabric. The tension around that loop is uneven, and if the loop is not constrained, it would unravel. But when these quarks come together and form a stable particle like a proton or neutron, their filaments connect in a triangular structure. This arrangement of filaments, with each one interacting and constraining the others, keeps the quarks stable and prevents them from scattering or separating. It's the intricate balance of these filaments that holds the quarks together. Now, let's explore what happens when you attempt to pull apart two quarks that are bound in such a structure. The process of pulling them apart isn't just about trying to separate particles. It's about stretching the tension between them. You're pulling on the tension in the energy sea, and the crack you create isn't a simple void, but a rapidly widening space that the energy sea can't leave alone. The system will immediately attempt to repair this gap by shifting the filament pathways, reconfiguring them into new patterns that restore stability. This restoration process results in the formation of new quark-antiquark pairs, effectively filling the gap created when you try to pull the quarks apart. This is why you can't isolate a single quark. It's an effect of the energy sea's natural response to the tension that arises when quarks are forced apart. On a larger scale, the strong force's behavior becomes even more apparent within the nuclei of atoms. Here, nucleons, protons, and neutrons don't behave like isolated balls pushing against each other. Instead, the energy sea's texture, the filaments and tension, form intricate pathways of forces that bind the particles together. The interaction between nucleons isn't just a push or pull. It's the result of the energy sea trying to maintain a stable configuration. The system works to minimize the overall tension by ensuring that the particles stay within a range where their tension is optimally balanced. At shorter distances, the filament's tension becomes so extreme that they push back, which explains why nucleons experience a repulsive force when brought too close. The strength of this force isn't just about the magnitude of the push. It's about how the filament's tension is distributed and adjusted to ensure that the particles stay at a stable distance. The result is a highly complex but highly efficient system that ensures stability at the atomic level. In this view, the strong force isn't some magical, mysterious force that is separated from the other forces in the universe. Instead, it's a natural consequence of the energy sea's underlying rules. Just as gravity emerges from the large-scale curvature of space-time, the strong force is a result of the intricate relationships between the filaments and the tension that defines their structure. The apparent separation of the four fundamental forces: gravity, electromagnetism, the weak force, and the strong force, can be traced back to the way we've historically divided them based on their distinct behaviors. In reality, they are all just different expressions of the same underlying principle. Next episode preview: Strong interaction. Why can't nucleons be pulled apart or pushed together? Tap follow, share it on New Physics, Clear Universe.